Hello everybody, in this video tutorial I will show how to do parallel programming in C++ with OpenMP. In my case I will use Visual Studio to do the tutorial, but in principle you can do the same things with other editors and compilers. So what is parallel programming? If you go right click on your taskbar and you go to Task Manager, Performance, CPU, maybe you see the overall CPU utilization, but you can also show the graph for the logical processors. Seeing multiple logical processors means that different parts of the same C++ code can be executed simultaneously by different cores. And we will show how to do this, which actually enables you to really exploit your CPUs. So let's create a new directory for the tutorial, YouTube tutorial. Alright, and let's open Visual Studio and create a new project. It will be a C++ project Win32 console application. Just place the folder in your directory and okay, let's name the project tutorial. Enter. Follow the wizard, leave precompile headers and console application. Alright. Alright. So first thing to do is to enable OpenMP in Visual Studio. If you use Visual Studio, OpenMP is already in your software. So here maybe let's put release and x64. In order to enable OpenMP, just go right click on your project properties, C++ language, and you have here OpenMP support, turn it on. Okay, then let's include some other library. So include IOStream first. Then let's include OpenMP omp.h, and finally include stdio. Alright. Then let's also define a variable that I need 8, n will be 8 in my case, and use name space std. Okay, at this point I don't want to waste my time and your time in to show how to create a function that prints the value of some variables. So let me just copy this function into my code. So this function is trivial, and it will simply print out the value of vector A and variables B, C, D, and M. Alright, so let's initialize variable I and then initialize vector A of size n, and then let's initialize to 0 B, C, D, and M. Alright, at this point I want to show to the terminal the value of these variables. Before, let's name these variables, attribute to this variable the value of before the parallel for loop that I will create afterwards. At this point I will use the function printvar and print out the value of A, B, C, D, and M. Alright. Then let me show now how to do actually parallel programming. So write pragma and then OMP parallel for, which means that the next for loop will actually execute it in parallel, each iteration potentially to a different by a different core of my CPU. So the index will be I, and then so I from 0 to n I plus plus. Alright. And what do I want to do in each iteration? So first I want to printf, so print out the value of the variables, and these variables will be OMP, so the number of the thread, OMP get thread, get thread number. Alright. And then I will also print I, B, C, D, and M. B, C, D, and M. Alright. And on the terminal I will display the thread number, and then iteration number, and then B equal to the value of B, C equal to the value of C, D equal to the value. Sorry, watch out, this is D because I want to print out all those integers, and M equal to, alright, M, and then new line. Alright, so if you don't know how printf works, I suggest you to search it on Google. So basically when printf finds in this string %d, it takes the value from this variables and it prints the values to the terminal in place of these strings. Alright, so we have first we will print the thread number, then the iteration number, then in the right order B, C, D, M. B, C, D, M. After this, I actually wanted to assign to A index I the thread number, this thread number. And the same thread number will be assigned to B, C, D, and M. Alright. After the parallel for, I want to print again the value of these variables. And finally freeze the console. Alright. However, before making a try, I still need to put some elements, some attributes here. And so first I want to write default none. So each variable within the within the for loop can be treated differently using in the parallel environment, and how each variable is treated can be customized. If I write default none, it means that I needed to specify how each variable is treated. For example, I want to say that a will be a private variable. No, sorry, private variable would be I. Then another private variable will be actually B. Then I want to specify that C is a first private variable. D will be last private. And finally, I will have shared variables M and A. Alright, but how do these specifications mean? They mean I actually made an image to let you understand. So here we have our private our parallel environment, and here is outside we have our code. So we defined the variables outside the parallel environment, but if for the parallel environment we define that B is private, then it means that the B inside each thread will be different from the B outside of the parallel environment. This means that in the parallel environment I will need to specify a new value of B. If a variable like C is first private, it means that in the parallel environment the variable C will be initialized with the value that it had outside the environment, but the result will not copy it back to C after that the last thread finishes. If a variable like D is last private, it means that the variable D, although it was initialized before outside the parallel environment, and we needed to initialize it again in the parallel environment, but the result of the first thread in D will be copied back to the value of D outside the parallel environment. If a variable is marked as shared instead, the parallel environment will have the right to access the value of M outside the environment. Okay, so what do we expect here? So if we try to compile this function, we are going to expect an error. And this is because D and B are not initialized in the parallel environment. Indeed, B and D are last private, and as we have seen here, B and D needs initialization because they cannot take the value that they had before. So we need to put here, for example, B equal to 100, D equal to 10. And this will let us compile the code. Alright, so at this point we can run the algorithm and see that we have different threads, 8 threads, because I have actually 8 logical CPUs. I have, of course, that B and D were initialized to 0. B and D 0, but they of course take the new value inside in the parallel environment. C is always 0 because the value of C outside the parallel environment is copied inside, and M can take a random it's not actually random, but can take different values. So if m is equal to 0 inside the parallel environment, since m is a shared variable, it means that for those threads where actually the first in time to be executed, because actually they could assess the value of m before that any other thread could modify m, the shared variable. So after the for loop, we can see that b is 0, and this is because b was private, so we couldn't copy the value of b inside the parallel environment outside. We have that c is 0, and we have that it is because c is first private, so it means that the value of c was copied from outside the parallel environment to inside, but couldn't be copied back to the variable outside the parallel environment. We have that d always takes the value of 7, because 7 is actually the last is always the last iteration, and we have that m is equal in this case to 4, and this actually can change from time to time. Here we have, for example, 5, and this is because m is a shared variable, so m just keeps after the parallel environment keeps the value of that was assigned by the last thread to be executed, or the last thread that could modify m. Instead, for d, so d is always takes the value of the last thread, but not the last thread to be executed, but the last thread in the order that was assigned by the schedule. So here we have that, as you can see, each thread takes one iteration, and thread number 1 takes iteration number 1, thread number 7 takes iteration number 7, and so also a, that is a shared variable, was modified by the threads, but each thread modified a different element of a, and we can see that since in this case each thread took the corresponding iteration, here we have that we get the thread numbers in a in the right order. Alright, so at this point I can show that this value can be changed to 16, so we actually have now 16 iterations to be executed by 8 threads. At this point we can see here from A that the values of the thread numbers are executed in the right order. So here we have that iteration number 0 and iteration number 1 are executed by thread 0. Iteration number 2 takes 4, and it should take 5 here, and so on. And we have number 1 that of course takes 2, and the other one, alright, number 3, so they are in the correct order. We see that in this case we get that so all the principles of remains for these results. Here we have m equal to 6. It means that the last thread that modified M was thread number 6. One thing that they didn't point out before was that before the parallel environment A just got random numbers because A wasn't initialized. Alright, then let's try another option that I can use for my parallel environment, and this option is actually schedule static 3. Alright, so let's try to run my program again. Okay, here we can see that we can only exploit 5 threads, and thread number 5 only takes 1 iteration, while all the others takes 3 iterations. And with schedule static we assume that the threads gets the iterations in the right order, and each thread can must take 3 iterations. All right, so we can also show that, and we can say that the schedule is not static but dynamic. All right. Dynamic usually takes more overhead, more variables passed in your RAM. And so we can see that in this case we also have 3 threads that are executed in parallel by different we have actually 3 iterations for each thread, but once that thread completes the execution of its code, then it can be reassigned before the others, the other thread, the other CPU finishes. So we can see here that we have a lot of zeros, and then we have 2, 3, and 5. This is actually because so probably thread number 0 finished before the other threads, so it was assigned, we could assign thread number 0 to twice double the number of the iteration. So thread number 0 with the schedule dynamic didn't have to wait for the other threads. Alright, so here if I run the program again, I can see that here I have a D equal to 7, M equal to 6, and another time I could get D equal to 1 here, for example, although I also use thread number 2, and this is because the last thread, so in this case I had that thread number 1 executed the last iteration. So also we with the dynamic option we have that is not guaranteed that thread are executed in the same order as the iterations. Here, for example, we have that we used the first thread number 2 and then thread number 1. So instead, if we had used the static, then this could actually not happen. Here we are forced to have that the thread are executed in the same order as the iterations, and so this also takes more time because the thread cannot be reassigned if they complete their task before other threads. Alright, so just one thing that I wanted to point out is that here you could also say that num threads was 1, and in this case if I run the program, then I can see that I can force my program to use only one thread. So I hope that this tutorial was helpful. Of course, you can also parallelize other commands different from a for loop, and but these are more or less all the options that you need in order to really exploit parallel programming. Thank you for watching this tutorial, and I will copy this code in the description of the video, and see you next time.